Hello everyone, welcome to today's video where we'll be learning more about metrics used to evaluate classification models. First, let's start with understanding what classification is. Classification is a machine learning task where the goal is to categorize input data into predefined classes or categories based on the features. So some of the examples of classification are classifying an image, like if the image has a dog or a cat, or even like there are audio classification where you can convert spoken words into text, and there is text classification where you can do sentiment analysis based on a Twitter data, if it is positive sentiment or a negative sentiment, and in medical imaging where you can use classification to understand if there are tumor cells or not, and even the environment sound classification, if there are multiple sounds coming in the environment, you can classify it as bird song or a dog barking, etc. So normally we relate classification models with metrics called accuracy. If suppose we build a model, we say the accuracy of the classification model is 97% or 95%. So what does accuracy mean? So accuracy is nothing but the number of items the classification model classified correctly versus the number of items it tried classification on. So it gives a percentage of how much correctly the classification models predicted the output. Let's talk about a scenario where we are designing a binary classifier to predict if an image is of a dog or a cat. And say we have two models, XYZ and ABC. So what does it mean when we say a model has 90% accuracy? So when we say we have 90% accuracy, that means on a given data set, 90% of the time a model predicted the output correctly, whether if it's a dog or a cat. And if suppose there are 100 images we have, so 90% accuracy means the model predicted 90 of the images correctly. And what can we infer about the data set when we say we have 90% accuracy? So just knowing the accuracy, we won't be able to talk a lot about what data was used, the number of dog or cat images that were used. And let's go to the next question. Like imagine XYZ has accuracy 90% and a model ABC has 84% accuracy. Can we say just because XYZ has 90% accuracy, which is more than ABC, that XYZ is a better model than ABC? Is there a scenario where the accuracy metric might fail? So let's take an example where we have 90 dog images and 10 cat images. And based on the earlier example, XYZ had 90% accuracy. So if we classify anything that comes into XYZ as a dog image, like no matter what image comes in, we still get the 90% accuracy for this data set because 90% of the images are dog images. So XYZ is hard coded. And let's take the example of ABC. ABC after training predicts for some dog images as dog and for some cat images as correctly cat. And the only problem is that it is not able to predict 16 of the images correctly. Hence, it has 84% accuracy. Now, with this information, we kind of understand that 84% is kind of much better than whatever XYZ was doing with 90% accuracy. And such data set where you have a imbalanced ratio of cat and dog images or two different labels is called an imbalanced data set. Let's take a real life scenario where such things might happen where we have imbalanced data set. So imagine we want to classify cancerous cells as cancerous or non-cancerous. So the data set that we might have will have largely images of non-cancerous cells. And when we are training the model, if we don't accommodate for the imbalanced data set, we might cause more harm than having a useful implementation of a ML model. Now that we have talked about how accuracy alone might fail, let's talk about what other things can we do during training. So to begin with, we can make sure that the data set is balanced. So there are different ways in which we can make a data set balanced. We can drop a lot of data from the larger class. or we can do data augmentation. Like if it is images, we can do rotation, flipping of images for the smaller class to increase those data sets. And even during training, instead of using normal loss function, we should use a weighted loss so that the model training can incorporate the data imbalance. And let's now see what metrics can be used if the data is imbalanced. Now let's take an example of a scenario where the accuracy metric might fail. So in the data set, we have image name, actual prediction, that is the ground truth, and the predictions from XYZ model and ABC model. Let's visualize how the data looks like. So this is the code to see how many dog or how many cats have been predicted by different models. So if you see the first graph, that is the ground truth or the actual prediction. So we have 90 dog images and 10 cat images. And the XYZ model, as described earlier, outputs dog no matter what the input is. So all the 100 would be classified as dog. And in case of ABC model, we have 80 dog predictions and 20 cat predictions. So now let's see how many of the classifications were correct from both XYZ and ABC. So if you see the graph, there are 77 dog images that were correctly predicted by ABC model and 7 images of cat. And when we see XYZ, it predicted all the 90 dog images as correctly. And so better way to visualize such outputs are using a confusion matrix. Let's see what a confusion matrix is now. So the first cell is true positive. Imagine when we are building a binary classification, dog is a true positive and not dog is the other case. So in the predicted value, if it is a dog and we predicted it as a dog, that's when we say it is a true positive. And imagine when it is a dog, but the model predicted it as a cat. So that's called a false negative. And in similar way, imagine if it is not a dog and the model predicted it as a dog. So that's a false positive. And for a case where it is not a dog and it predicted as not a dog, that's called a true negative. So this will be easy for us to visualize how the model is performing. Let's go ahead and see how the confusion matrix looks like for both ABC model and XYZ model. So if you look here, the confusion matrix for ABC model, we have 77 dog images that were correctly predicted and 7 cat images that were correctly predicted. And for the other cells, for a cat image, it predicted as dog. There are 3 such instances. And in the same way, for 13 of the dog images, it predicted as cat. So that is why we have 13 on the top right cell. Let's see how the confusion matrix looks like for XYZ model. It could only predict, so if you see here, it could only predict 90 of the dog images correctly. It didn't predict anything as cat. So for the classification of cat, if you see here, as we know that the XYZ model always outputs the label as dog irrespective of whatever the input is. So it could predict 90 of the dog images correctly, but it labeled 10 cat images as wrong. And for the cat section, it is 0, 0. From this, we get an idea that the model is not working well for a cat label. Now, let's look at how we can use these values for our metrics. Precision and recall are two new metrics that can be used instead of accuracy. This will give us a better idea about how the model is performing. So let's take precision. Precision is nothing but out of all the images where the model predicted image to be dog, how many were actually dog? That is true positive by true positive plus false positives. And recall tells you how many of the relevant items were retrieved. For example, out of all the dog images that a model got, how many were actually predicted as dogs correctly? So these are precision and recall. This will give us a better understanding of how the classification works for each individual label instead of checking it overall. So this is just the calculation of how we can do precision and recall. So repeating of all the positive predictions, how many were really positive? That is precision. And of all the real positive cases, like of all the real dog images, how many were predicted as a dog? That is recall. And along with precision and recall, F1 score also gives you an idea of how good a model is doing. And F1 score is nothing but a common harmonic mean of precision and recall. Now let us see how the precision and recall are for the models ABC and XYZ. So these are the precision and recall values for model ABC. So if you see here, it gives us an idea of how good the precision and recall is for dog and for a cat. And a good value for precision is 1. The precision and recall ranges between 0 and 1. And 1 means it did a perfect job, and 0 means it didn't work correctly. So for XYZ model, so if you see here, the precision and recall for cat is 0. But when you compare with the precision and recall of dog for ABC model and XYZ model, XYZ is doing a pretty good job. So using precision recall, we can understand how the model is working on an individual label. And again, so F1 score, if you see here, F1 score of ABC model is 0.8399, and for XYZ model, it's 0.9. So since the data set is imbalanced towards a dog images, we should use the weighted F1 score. And when we see the weighted F1 score, ABC has 0.861 and weighted F1 score of XYZ model is 0.852.